Pleasure to introduce Csaba Biro from Louisville. He's going to talk about interval orders and polyhedra.
Thank you very much. I also would like to thank you for the opportunity to be here, and not only at the seminar, but I really appreciate the University of Costa Rica to host me for these last almost 3 months. I had a great time here. This is a great place to do mathematics. So thank you very much for all of these opportunities. So as I said, as Oscar said, I'm going to talk about interval orders and polyhedra. And this is joint research with Csaba, who is my PhD student, graduated in 2022. And the story is that we started this work together, and actually the first part of the presentation is going to be part of his work. And after that, Andrei Kasdi, who was one of my colleagues, he was on the committee, on his PhD committee. And so he got interested in the problem. And then we started to work a little bit together. Jan and Leha joined us. And then we had some other results, interesting results later, which turned out to be a little bit different from what we did with Csaba, but that's a good thing. So I will talk about both of those things. Okay, so I'm assuming here a general mathematical audience, so I wanted to define everything here just to make sure. So what's a partially ordered set or a coset? It's really two things. It's a set and a relation. And the relation is really a subset of the product of the set by. It's a set of ordered pairs of the set X here, which is what we call the ground set. And this relation is reflexive, anti-symmetric, and transitive. And I underline transitive because that's really the important part. Because reflexive or not, I mean, you can always change that, right? You add the reflexive relations or not. Anti-symmetrics, what if it's not anti-symmetric? Okay, now you can have pairs that are, one is less than or equal to the other is less than or equal to the first, but they're not equal. Okay, big deal? Not really. These pairs actually form equivalence classes, and if you factor out that equivalence class, now you have partially ordered set. So it's really the transitive is what we really study. So what we see here is a Hasse diagram, okay, so I guess my pointer doesn't point.
Oh,
yeah, that's fine.
Yeah.
So what we see here is a Hasse diagram, which is a typical way of representing a poset. And what we have here is in this drawing is that the points of the ground set are represented as points on the plane. And then if an element is greater than another one, then it's up from the previous one and connected. So in this picture, J is greater than G, but D is not, even though it's higher, but there's no actual path from G to D going all the way up. So this is, in some sense, a simplified diagram. It's a way to represent posets visually. So, yeah, okay. So special posets. If a poset has the property that every pair of elements is comparable in it, we call it a chain. We also call it sometimes a total order or a linear. And this we also apply this subposets. And antichain is the total opposite when every pair of elements are equal. So the longest chain in the poset is what we call the size of that is what we call the height of the chain. It's denoted by H of P, and W of P is the width of the what did I say? The height of the poset, right? Is the maximum size of the chain, and the width of the poset is the maximum size of an antichain. So going back to this previous picture here, H, A, J, D is an antichain, for example. There are others, you don't have to be on the same level, right? I and J form an antichain, or IJD form an antichain. The width of this poset, I believe, is 4. Probably you can't find an antichain of more than 4.
No, but it would be 5.
Would it be 5? Where is
JD,
I, A, J, D, and B, right? Yeah, 5, at least 5. Maybe somebody can find a 6 or an antichain, right? But the height is 3, right? Which would be just the size of the longest chain. So as you might deduce, I'm mostly interested in finite posets, because for infinite posets, these numbers can be infinite. And in fact, if you ask mathematicians who are not combinatorialists, what do they know about posets? I'm guessing that they would probably say Zorn's lemma and maybe Dilbert's theorem. Zorn's lemma is of course only interesting for infinite posets. It's equivalent to the axiom of choice, and for finite posets, you can actually prove it from the rest of the axioms. And it's pretty trivial anyway for finite posets. And Dilbert's theorem is the theorem that says that if you have a poset, the number of chains that's required to partition the poset into, if you want to partition the elements of the poset into chains, how many chains do you need? Now, you are going to need at least as many as the width of the poset, because in an anti-chain, there is no way you can put 2 elements into the same chain, right? But Dilbert's theorem is the theorem that says that that's actually sufficient. Now, even though Dilbert's theorem is very important for the combinatorics of posets, these are not the topics of this talk. Okay, so what is the topic? Okay, interval orders. This is special posets. So we have a function now from the ground set of the poset into the closed intervals of the real line. We call this function interval representation if it has the property that whenever you have 2 elements in the poset, x and y, and x is less than y, then the image of x is entirely left of the image of y. Entirely left means also disjoint. And entirely left is just means that the right endpoint of fx is less than the left endpoint of fy. And we're talking about strictly less because these are closed intervals. We really do want them to be disjoint. Not even the point of intersection is allowed. And this is an if and only if. So that means that if 2 elements are incomparable in the poset, then their intervals must intersect. Not every poset has an interval representation. A poset is an interval order if it does have one. So the first natural question, and this probably was asked early on by mathematicians who started to study this, what are exactly interval orders? How can, if I give you the Katz diagram of something, can you just tell me if it's an interval order? And first observation, we can see that this poset that's depicted here, we call it the 2 plus 2, is not an interval order. Now, why not? Well, I don't know, maybe this is the technical issue that I want to draw something. Is that okay?
Yes.
Okay, so what can happen here is that if you try to make an interval representation, what would be the image of A? Well, it's some kind of closed interval, right? What would be the image of B? Well, B has to be entirely right of A. So it's somewhere here. Okay, I don't know the length or the distance between the two, but the picture kind of looks like this, right? I'm a little hand baby here. Where is C? Well, C is incomparable to both A and B. So I know one thing, it has to definitely overlap both. So it has to go between these two and then extend to some distance. Maybe not at all, maybe it starts here and it ends here, or maybe it extends the long way. So I'm not going to draw the tick marks at the end because I don't know where it ends, but it looks something like this. But one thing is clear now, if you want to put D on the picture, it has to start after C. So no matter what you do, it's going to be greater than A. And if it's greater than A, then you have a problem because it's not in the poset. So that's a simple observation. And the beautiful fact is that this is all you have to exclude. So Fishburne's classical theorem is that the poset is an interval order if and only if it has no 2 plus 2 subposet. It also has a beautiful proof, which is, I don't think Fishburne's original is that one. Greenough, who was a student of Kenneth Bogart, wrote a PhD thesis. I don't think it appeared in a paper, but in his PhD thesis, he gave the proof from the book. Yes.
Those 2 plus 2 subsets would mean that there are disconnected chains.
Yes, it's you can say just two. That's all I need is 2 chains. Each of them has 2 elements, and the chains themselves are totally incomparable to each other. Yes, that's the 2 plus 2. So when I say subposet, maybe if you're thinking in terms of graph theory, you could, some people call it an EU subposet, but I just call it a subposet. It does mean that incomparabilities are also enforced. It's not simply order preserving bijection, but it's actually it preserves comparabilities and incomparabilities. Yeah, so okay, because if it has a 2 plus 2 subposet, it obviously cannot be an interval. But now this theorem is saying that if it doesn't have one, then it is actually an interval. And I show you a little bit of a schedule. Yeah, I'm gonna have to watch it. I'm gonna show you how to a bit of a sketch of a proof with a lot of details missing here, because it's so beautiful. So here's what happens. Let's first use a couple of notations. Dx, we call that the down set of x, is all the elements of the poset that are less than x. That does not include x. And ux is what we call the upset, is all the elements of the poset that are greater than x. I use this calligraphic D to denote the set of downsets of a poset, and the calligraphic U to denote the set of upsets of the poset. Now you might think first, when you first look at it, wait a second, so calligraphic D just has the same number of elements as P, right? But it's not true, because sometimes these downsets coincide, right? So you can have two different elements with the same downset. And they could be significantly different elements because they can have different upsets, but the same downset or the other. So it's actually going to be typically smaller. These are going to be smaller than the poset itself, the size of the poset. So this is an easy claim that if the poset doesn't have actually that this calligraphic D and calligraphic U are total orders, and the poset has no 2 plus 2 are all equivalent statements. The first two are clearly equivalent because the definition is dual. You can just turn the poset upside down, and then from one you can get the other, right? Everything is symmetric for the definition. But the last one is that if the poset has no 2 plus 2, then these are total orders. And if it does have 2 plus 2, then these are a little short exercises. They're not actually very hard to prove. But here is the interesting part. They are the same size. And as I said, this is not trivial because their size is not the size of the poset. It's typically smaller, but they still have the same size. And you might think, oh, that's probably easy. Let's just quickly make a bijection and maybe you try something natural, but it's not that easy. Okay. So
it doesn't follow from inverting?
no, because the poset can be, it doesn't have to be self-dual, right? So the upset and the downset could be very different from each other. You can have, say, 3 elements that are minimal and only one maximal element. Okay, so all the minimal elements have its downset is the empty set, right? So now you have 3 copies of those, but then in the upset version, you only have 1 copy of that empty set. So now, how many did you lose from the whole set? It's a different number. And if you try something natural bijection, like let's say, I don't know, most people think that maybe let's take an element X, it has an upset, it has a downset. Let's just make a bijective relation of those. Is that a bijection? No, it's not. It's not gonna work. So it's more complicated than that. But anyway, it's still, I mean, actually, if you're bored of doing this talk, you can think about the proof. There are different proofs, multiple different proofs. And again, it's not super hard, but it's trickier than just, I can't say it's true. Okay, so what you can do is you can order these upsets and these downsets because they form this total order by inclusion. And then you can number them, and the key part here is that this M is the same for both cases because it's the same number. But we order them opposite way. So we order the downsets increasing and the upsets decreasing. And the reason we do that, because what I want to show you is that if you have a poset with no 2 plus 2, I want to show you why that's an interval order by actually giving you an algorithm is how to find that function, that representation function. And here's how you do it. Take the element of the poset and then find its downset on that list somewhere, find its upset on that list somewhere, look at the indices you get. Those indices will tell you the interval to use. So A is going to be assigned to that interval ij. I is the index of the downset, and j is the index of the upset. Why does it work? Well, it's a proof. It's not obvious. It works. This representation uses integer endpoints from 1 to m. That m is, as I said, it's not typically the number of elements of the poset. It's typically less than that. It's called the magnitude of the interval order. And it has the property that it uses the least possible number of endpoints of all representations and distinct endpoints. And also, we call this the canonical representation. Later, I found, I always thought that this was a well-established name, but recently I found some papers where canonical representation was used something different, but I'm going to use it for this one. So this is an example. This is actually from the undergraduate textbook of Keller and Trotter, School of Applied Combinatorics. If you teach a class on this, it's I think it's an excellent textbook. So this is the example I stole from that book. And here I listed the downsets, I listed the upsets, and you can see actually the sizes are not even the same, right? You have a 4-element downset, but you don't have a 4-element upset, for example. And so, but the number of them is correct. So when you want to find, for example, what interval should I use for the element A, what you do here is to find the downset of A. Hope I didn't mess this up. Actually, I just should have looked at their solution from the book, but I didn't. I actually worked it out myself. So the downset of A is CFG. You find CFG on the list. That's number 3 on the downset list. Now you look at the upset of A. What is that? E, right? You should find E on the list, number 4. So 3, 4 is the interval you will assign to A. And it turns out that some intervals will get the same. Some elements will get the same interval. For example, A and J will get the same interval. Both are getting 3, 4. Now, why is that? Clearly, because they have the same upsets and the same downsets. A and J, they both have the same upset, which is E, and they have the same downset, which is CFG. So this actually happens 3 times in this poset. We call these elements duplicated holdings. And for certain studies of interval orders, we can kind of forget about them. We can often assume that they don't exist because you can remove one, and the posets properties, some properties don't change fundamentally. Okay, so semi-orders. What are semi-orders? An interval order is a semi-order if it has a representation where every interval is of the same length. Usually we say it's of length 1, but obviously if you change the length, it's same definition. Now, what are semi-orders? An interval order is a semi-order if and only if it contains no 3 plus 1 subset. What's 3 plus 1? It's a 3-element chain, and then just an element. It's a 1-element chain, and the 3-element chain is incomparable to that element, every element of the 3-element chain. Why is it not a semi-order? Well, I tried to draw it, try to draw the intervals for it. A 3-element chain will have to be 3 intervals, like in the first row here, first line here, going one after the other. And then you have to draw the 1, right? The 1 has to overlap all 3 of them because it's incomparable to all 3. You can't do that. This picture is cheating. The middle one is a little shorter. But if you wanted to make all of them of the same length, it's just simply geometrically impossible. But if you want to write down the inequalities, it's pretty obvious too. So 3 plus 1 is not a semi-order. So what's the immediate question of a mathematician here? Is that all you need to exclude? And the answer is yes. This is the theorem of Scott and Suits, also a classical theorem. In fact, yeah, I already wrote it here. An interval order is a semi-order if and only if it contains no 3 plus 1 subposet. The other part is a little more complicated again, but it's not too difficult. All right, so what did we study? This is all I showed you until this point, well-established mathematics. Everything here was known by the 1980s, I think. But here starts here starts the new stuff, but first I have to give you a couple of definitions. So linear order is a linear extension of the poset P if it's a chain, it's a linear order and an extension of P. Now, what's an extension of the poset? You just add more relations. You have to preserve transitivity, of course, but other than that, you just add relations and it's still a poset, it's called an extension. And if now at the end every pair of elements are comparable, then we call it a linear extension. By the way, it's completely obvious that every finite poset has a linear extension because you can keep adding elements and you run out of incomparabilities. For infinite posets, it's actually equivalent to Zorn's lemma. Definition. So we have a set of linear extensions is a realizer if they have the property that the intersection is the poset. Now, what does that mean? So if you have two elements x and y in the poset that are comparable, x is less than y, then every linear extension, it has to be the same. X must be below y. But what if you have two incomparable elements? Then you can have either this way or this way, right? Either way. You can order them either way in a linear extension. Now, this definition says that if you have a realizer, then in the intersection, neither of these pairs appear, which means that it has to be ordered one way in at least once and has to be ordered the other way at least once. And that means that in the intersection, it just disappears. So, yeah, yes.
When you have a linear extension, you just add relations, or sometimes you need to add points?
No, it's the same set of points. Yes.
Okay, you keep the set of points and you just add relations.
Yes, yes. So what I didn't define here is the word extension here. Extension means that it's on the same set of points. Yeah. Okay, yeah, very good question. So, does every poset have a realizer? Yes, you can, at least for finite posets, as I said, we talked about finite posets here. It does have, and actually that's true for infinite even. You can just take the set of all linear extensions, that must be a realizer. But the challenge is to find a realizer, that's what I just said. To find a realizer which is small. So you don't use too many linear extensions. The minimum number of linear extensions you must use for a realizer is what we call the dimension of the poset P. So dimension is a parameter of poset that's studied a lot. It's also probably 100 years old now because Dushnik and Miller defined it in the early 20th century. Don't remember exactly the date of their paper, but it's getting, if it's not 100 years old, it's probably getting close to that. Chains are dimension 1, and those are the only one-dimensional posets. That's pretty obvious. What about antichains? Antichains are of dimension 2. Why is that? Well, you take an antichain, you order the elements in some way, and then you order the elements in the exact opposite way. Those are two linear extensions, and now you take the intersection, it's the poset itself, so they're dimension 2. So are there large dimensional posets? Yes. This is a very important poset. It has this one has 10 elements, right? 5 minimal and 5 maximal elements, and it's not. It almost looks like that all the minimal elements are less than all the maximal, but it's not actually right, because here, if you look at this picture, A1 is actually incomparable to B1, A2 is incomparable to B2, and so on. So you can say B1 is less than every element except for its mate on the other side. And why is this? This poset here is actually 5-dimensional because it has 5 elements, but you can generalize it for n, and then it will be n-dimensional. Why is that? Well, if you look at linear extensions, because A1 and B1 are incomparable, there has to be a linear extension in which B1 is over A1. Okay, so in that linear extension, A2 will be over B2, right? Because you remember I said B1 is over A1. So that means A2 will be somewhere up and B2 will be somewhere down. So you can't swap the A2, B2 in the same linear extension. Also, you can't swap the 3, the 4, the 5. So you can only swap the A1, B1. If you do that, you can't swap over any of the other ones in the same linear extension. So that means all 5 of these pairs in this poset will require its own dedicated linear extension in any realizer. That means you need at least 5. Now, we just proved that the dimension is at least 5. Why is it at most 5? It's at most 5 because you can actually construct a realizer, not too hard. Okay, so we have large dimensional posets. In fact, the dimension problem is a difficult problem. In general, it's an NP-complete to determine if the dimension is less than or equal to k for k greater than or equal to 3. I don't remember the result for 2. I think it's 2. Yeah. Don't remember that now. But it's for larger k for sure. It's NP-complete. And okay, so another interesting thing about dimension is that it's the least positive integer t for which p can be embedded into RT. This is actually what the explanation of the name. We're not going to use this fact directly here, but this is why it's called the dimension of the poset. And also, if you familiar with the hypercube or the Boolean lattice, which is a special poset of all the subsets of an n-element set ordered by inclusion, this poset here is a subposet of that. So it will also show that the n-dimensional hypercube is also actually dimension n in this sense, or at least dimension n, and actually it's also at most. For example, you can use this last statement for that. Okay, so that's dimension, some basic facts about dimensions. Now, how about interval orders? What is their dimension? They don't have this SN posets. Yeah, these posets are called SN. They stand for standard example. Who came up with that name? I don't think it's very good, but it's too late to change it now. So that's the end. We call that something standard example of dimension 5 or S5. And interval orders do not have these. Why? Because if you look at this poset is full of 2 plus 2s. Even for n equals 2, the poset itself is just a cross, which is just a fancy way of drawing a 2 plus 2, right? So once n is at least 2, it does not have, interval orders do not have Sn. So maybe interval orders are all small dimensional. No. In fact, there are large dimensional interval orders, not only that, but we have this property that an interval order dimension, if you define this interval order, which we sometimes call the universal interval order, when you take every pair of positive integers between 1 and n and make an interval out of them. And this allows I equals j, so that means you have the trivial interval, which is just 1 point. That's also a closed interval, right? You take the poset that's represented by these intervals, the dimension of this poset will actually converge to infinity when n goes to infinity. And I did type out the proof of that. I don't know if maybe I should show you this because it's simple and beautiful. Just the fact that it goes to infinity. The dimension is actually known for a large precision, but that's more difficult. So why is it going to infinity? You might be familiar. I always have trouble figuring out in a colloquium what people know. This is the hypergraph Ramsey theorem. So probably you are familiar with the classical Ramsey theorem, graph theory, that when you say you have a graph on n elements and you two-color, well, you have a okay, here is the question. You two-color complete graph, the edges of the complete graph with red and blue colors. If the graph is large enough to start with, then you will find a large monochromatic clique in that graph. That's the classical Ramsey theorem. The hypergraph version is that, well, in this case, you can do R coloring, but you can do R coloring in the graph version. But in the hypergraph version, you're actually coloring certain size subsets of an n-element set. So here we're coloring the k-element subsets of the set 1 through n. And if we do that, if n is large enough, then you can find a monochromatic subset of whatever size you want. What is a monochromatic subset here? A monochromatic L-element subset would be a subset where every k-element subset of that subset is of the same color. So that's the hypergraph Ramsey theorem. So what we will do to prove that the dimension of I goes to infinity is to assume it doesn't. So if it doesn't go to infinity, then well, actually that's not what we will actually prove. It's unbounded. Okay, I just realized that there's this possibility of jumping up and down, right? And it doesn't go to infinity in that case. So we'll actually get the contradiction that is bounded. So that's wrong. That's not what we will prove that the dimension is unbounded. So okay, suppose it's bounded. Suppose that the dimension is not more than d ever. Okay, now we use the hypergraph Ramsey theorem to pick an n, a large enough n, for this d, as for d is going to be the number of colors. And we will use k equals 3 and l equals 4. So that means we're coloring the 3-element subsets, and we're going to find a 4-element monochromatics subset in this coloring. So we take a realizer because, yeah, it's d-dimensional. So that means at most d-dimensional, that means there exists a d-element realizer. If you don't have enough linear extensions, you just pad it up. You just write a couple of linear extensions twice. That's fine. You can always do that. So it's kind of, okay, there's a little cheating here, right? It's a Moore set, but don't worry about that. And then for every triple ABC, the way we will cut, what we will do, we will have to, we do have a color for this ABC, right? We can define a color because the theorem says that for every coloring, there is going to be a monochromatic subset. So what is my coloring strategy? My coloring strategy is that I look at this interval AB and BC. Now, notice that these are incomparable because they have the common element B, right? But they're barely. You have AB here, and then the BC starts right there. So they're barely incomparable. So I'm going to actually look at the linear extension in which they are the wrong order, in which AB is greater than BC. I'm calling it the wrong order. There's no wrong order, but it's the opposite of the almost order of ABC. And then I'm going to find a linear extension, and that linear extension is Li, so I will use that color I for the triple ABC. Now I know from hypergraph Ramsey that I have a monochromatic subset of this n set. Let's find it. Let's say it's XYZW, and look at its color. It's color J. So this is a monochromatic subset, which means XYZ and YZW are 3 triples that got the same color. But if XYZ was colored J, that means in Lj, XY must be greater than YZ. And if YZW has color J, that means YZ is greater than ZW in the same Lj. But that's impossible because ZW is actually greater than XY in the poset, so you can't order them backwards in the extension. This is a pretty technique that's used quite a bit in these kind of proofs, and it shows that interval order dimension is unbounded. It doesn't actually show it goes to infinity, even though that is true. It's actually known that it's log n plus a little o of log n. No, actually, I think it's log n plus 1/2 log n plus, yeah, plus a small term. I think that's what's known now. There's a sequence of papers in which they prove better and better approximation. And at this point, we know the dimension of this poset pretty exactly. I think Trotter told me that if you put together every paper, you can determine the dimension with an error of at most 5 or something. Okay, so what is the dimension of semi-orders? Well, they're not large. The semi-orders are always dimensional at most 3, and there are a bunch of proofs of this, but I probably should skip this part because I'm running out of time otherwise. So the semi-orders are dimensional 3. Okay, they're much simpler than interval orders. Okay, so it's a natural question. Interval orders are large dimensional, semi-orders are small dimensional. What can we say about things in between? So we can set a set of non-negative real numbers and say S representation is a representation of a poset when every length is in S. So this is just the notation that we will use. C of S is the posets that have S representations. C of AB is the set of posets for which the representations use interval sizes strictly between A and B. CA is C1A, it's just a shorthand for that. And if instead of C I use OC, then we are allowed to use both open and closed intervals. That notation will come up only once in this whole talk, I think. So the interval count of a poset is the fewest number of lengths that you must use to represent the poset. This is something well defined for finite posets, right? Because if nothing else, you just take any interval representation, you count the number of lengths you used. So that's at most what the count is in any representation. And then there has to be a minimum, right? So what is the minimum size of number of interval lengths you have to use to represent the poset? So interval count 1 posets are exactly the semi-orders. Semi-orders are interval counts 1, I mean, that's the definition, right? Basically the definition. What are the posets that are interval count number 2? Interval count 2. Well, that's a good question. There is no good characterization. And when I say there is no good characterization, maybe we would expect, okay, maybe there is a large list of forbidden subposets, but we just don't know the list. Well, actually, even that's not true. Fishburne proved that there is no finite forbidden family of minimal subposets. In fact, he constructed a list, an infinite list. All of them are minimal posets that are of interval count k. For actually, and he did it for every k. For interval count k, these posets are not interval count. If they're minimal, if you remove a single element, they will be interval count k. And it's an infinite family, so there is no characterization with the excluded finite family. Seems like a difficult problem. How difficult is algorithmically? We don't know. Could be polynomial, could be empty complete, but neither of them is proved. We don't actually know. This is one of them. Seems to be a difficult problem. And in fact, this was one of the motivating factor of the research that we did with Kesby and Lehel, is that we tried to. This is one of the things we try to figure out, even just for 2. Okay, so back to the paper that we had with my PhD student. So he found this paper, Kellogg, Frank, Young. At that point, it wasn't published; it was still on archive. And this paper proved 2 main theorems. The 2 main theorems is that the first one is that if you are allowed to use open and closed intervals, but all of them are length 1, the dimension of the poset is still at most 3. And then another one, if you're allowed to use just interval lengths 0 and 1. So now you have 2 different lengths, right? But they are very restricted. You're only 0 length for 1 length interval, then the dimension is still at most 3. So here you're adding open intervals to semi-orders, and here you're adding intervals of length 0 to semi-orders. And they proved in both cases that it doesn't increase the dimension. And they asked a couple of questions. So good PhD student, right, looks at the question or sees a question, they want to solve it. So they asked, if you have positive length, what is the upper bound? Can you find a good upper bound on the dimension of these posets? Second question, do you have a good upper bound for the dimension of k-count posets? And the third one is, how many interval lengths do we need to make a 4-dimensional poset? Now, Csaba answered all 3 in some sense. Well, okay, I think the third one is, he didn't answer that, but actually Kes did. So the first one, yes.
I have a question.
Yes.
What do you mean? How do you get intervals of length 0? Is that from isolated points?
Yeah, so a single point
Okay.
in which the left-hand point and the right-hand point is considered to be a closed interval. Because what's an interval? An interval is just a connected set of the real line. And then if it's a closed set, then it's a closed interval, and a single point satisfies that.
Yes, but I mean, how do you get the representation? When you have your poset, each elements map into.
So how is there an algorithm that gives you this representation?
Exactly.
Oh, that's more complicated. I don't even know if there's a simple good algorithm for that.
Okay.
Yeah. If you tell me which intervals you want length 0 and which intervals you want length 1, then it's a linear programming problem. But other than that, if not, I think this might be very difficult. And they actually didn't prove didn't do anything of that kind. They just actually showed that the dimension is at most 3. They're not even completely constructed in their proof. So it's not like even you can kind of follow the proof and construct the linear extensions, but the way they wrote it, they just cited other theorems that showed the existence of certain linear extensions, and that's what they did. Yeah. Okay, so this is the first theorem, and answer to the first question, and actually first 2 questions. If the interval count is at most k, then the upper bound is 2 times log k plus 3, at most 2 times log k plus 3. Now, how good is this bound? We don't actually know. For k equals 2, this gives 5. In the original paper, they gave a simple argument for 8, so we improved them in 8, right? It's 5. But and we know it's at least 3 for k equals 2. Just for k equals 2, we know it's at least 3 because semi-orders are contained in the class, and it's at most 5. So what is it? And by the time Csaba graduated, we didn't know the answer. But then Casdy is very good at computers and programming, and he actually used some kind of state-of-the-art dimension finding algorithm that he implemented, and he found the 4-dimensional 2-count concept. So we know that the lower bound is at least 4. But his example is complicated. It has 45 points and irreducible, meaning you remove any of those 45 points, it's going to go down to 3 dimensions. So that's kind of crazy, right? Yeah, so we still don't know if the answer is 4 or 5, but it's 4 or 5 for k equals 2. And then when k is large, the gap is growing. So because I think time issues, I'm going to completely skip this proof, even though it's nice, but the paper is on our. Second theorem, this is not from their paper, it's not from the Chankian paper. It's another question. In this case, what we asked, do we have a dimension bound on a poset in which the length of the interval is restricted between 1 and t, but you can use any number of lengths you want. So there is no restriction of how many different lengths you are allowed to use, but every length has to be between 1 and t. And interestingly, we get a much better upper bound in terms of t for that, because it's gonna be double. So the proof is, I think the paper is very nice because we developed a bunch of techniques at the beginning of the paper, and then we use those techniques to prove all these theorems in like a paragraph or 2 after the techniques are done. But the techniques are take some work to do. So yes, it's a double logarithmic bound. This is, by the way, best possible in terms of, maybe I wrote this down. Yeah. So for t equals 2, this gives a 4. But we actually, in this case, we couldn't actually find a 4-dimensional poset in C2. So Casdy's example for the other one is not in C2. In that example, we used the length 1 and length 8 intervals. C2 could not use both, right? So we don't know if there's a 4-dimensional poset in C2. We have this is a very small result, the second bullet point here. If every interval is of length 1 except for 1, which is allowed to be longer, then the dimension is still at most 3. It's a lot of work for such a weak result, but it still takes a page to prove it. And then the third is that this bound is best possible in terms of rate of growth, because what I mentioned about the universal interval order, for t, for like the IT, is in CT, and it's of dimension log t plus some smaller terms. So the log t is correct here. The 2 may not be, and actually I suspect it's not. I think that there's probably a proof with a bound of 1 there. Okay, so after this, so maybe do I have 10 more minutes? Is that okay? Okay. So what we did, so Siddharth graduated and went on with his life to make a lot of money, good for him. And then the poor stayed at the university to not make so much money, but to have a lot of fun with mathematics. And so we started to think on a little bit of different terms. So what about characterizing these K-count posets? And so one thing to recognize, and this has been known before us, is that the poset representation problem can be phrased in terms of linear programming. So what's linear programming? Linear programming is a problem of, it's an optimization problem. When you have a bunch of inequalities, all of those are represented by this matrix vector equation, right? A is a matrix multiplied by the vector x less than or equal to b, which is a vector. So that's a bunch of, I said equations, but inequalities. It doesn't really matter, you can do equations, it can be shown that it's equivalent. And we usually assume that the x vector is non-negative. And then at that point, you just want to maximize some kind of dot product, some kind of linear functional from Rn to R. And that's what the linear programming problem is. It has a history in operations research, military applications from World War II, getting resources to the front. And I don't know, very famously, Danzig found a simplex algorithm that solves it pretty efficiently, but there are a couple of problems and it's still not known if there's a version of the simplex algorithm that will solve it in polynomial time. However, the question, the problem itself is polynomially solvable. There are algorithms now, ellipsoid method, inner point method, in which the problem can be solved in a polynomial way. Now, in this general version, there is nothing about integrality assumed. If you say the optimal x is required to be an integer vector, so you're restricting your search space to integer vectors, then it becomes a difficult problem. So the interval representation problem is an integer linear problem. So it's not like easy, but the integrality here is not too restrictive actually. So why is it a linear programming problem? Well, if you're given a poset, how do you find an interval representation? What you can do is you can create three variables, Lx, Rx, and ρx for each element of the poset. These are going to represent the left endpoint of the interval corresponding to x, the right endpoint of the same interval, and rho is going to be the length. And so we can write down the inequalities that are required to be satisfied so that this is a representation. What are these requirements? Well, the first equation here just says that the length of the interval is the right endpoint minus the left endpoint. Great. And the length has to be non-negative, right? Otherwise, it's not really an interval. And then this one says that if you have two intervals, x less than y, then Rx is less than Ly, which is just saying that the interval for x is entirely left of the interval from y. Okay. And then the third one says that if they're incomparable, then the second one is not true either way. So it's going to be Ly less than or equal to Rx. And there's another version, which is x and y is replaced. But if you think of x and y as an ordered pair, then you only have to write one, and then the other one just comes out when you swap the variables. If all of these inequalities are satisfied for these variables, and you find a solution to this linear inequality system, then you get a representation, right? Great.
I didn't understand what the lower line means for each x.
Oh, that's incomparable. Sorry, yeah, I forgot to give you that. If x is incomparable y, then you have to have this inequality for that pair. And actually, it's also true backwards. Lx has to be less than or equal to R.
Okay, of course, because you need that.
Yes. You need them to intersect.
Yeah.
Right. So okay, or you can also just think about this is the negation of that inequality, right? Basically, yes. So okay, this is not a linear programming problem. Why not? Because of this strict inequality. Linear programming cannot deal with strict inequalities. So we have to change it a little bit. So what do? Okay, so this is not going to, okay, so linear programming problem, this is some basic geometry, right? These can be thought of as hyperplanes in a three-dimensional space. And so these inequalities are saying that your point, that's a solution, is going to have to be one side of the hyperplane, right? So if you take these hyperplanes and then you require your whole set to be on one side for each of them, or maybe if it's an equality, then we have to be on the hyperplane or on that subset. Then what you get is a convex polyhedron in three-dimensional space. But it's not going to be closed, so linear programming cannot deal with this. So what we do to remedy this is we add this +1 here, which will and that should be as an equal to, yes, sorry. Yes, so you make that +1 there, and that will add the additional requirement that now every pair of intervals have to be of distance at least 1 from each other. But that's usually not a big deal, because that can be assumed just by scaling up the whole representation. So now this is how you connect it to linear programming. So this is why I said if you ask me to find a representation of a coset with length 1 and length 0 intervals, and you tell me that I want these points to be length 1 and these points to be length 0, I can just write down this integer programming problem. I ran an algorithm solver. There are very efficient solvers in computer algebra systems nowadays. It's not going to be strictly polynomial because you want integer solutions here, but it's going to be pretty efficient to find one. Okay, so easy problems. If P is an interval order, if and only if this polyhedron is not empty, and yeah. And this is because, and when I say R is not empty, I'm talking about integer points. And every interval order has an integer representation. So again, this is not this is why it's true both directions. Now, if you want to detect if P is a semi-order, it's still easy. You can just add the equations rho x equals 1, and it's still easy. Now, not that it wasn't easy before, because we know there's a simple polynomial algorithm to detect if something is a semi-order or not, right? You can just take every 4 tuple and check if it's a 3 plus 1. If none of the 4 tuples are 3 plus 1s, it's a semi-order. Great. And that's n to the 4th, right? Operation, so that's very much polynomial. Okay. You can add an objective function to optimize this, but really, you notice that when I said linear programming, I didn't actually optimize for anything. I just want to determine if there exists a solution that satisfies all the inequalities. So if you want to add an objective function, you can do that. And here's what I wanted to say. So what we were interested here is we wanted to say, okay, so if we understand this polyhedron really well, maybe now we will be able to tell when is there a representation with only 2 different interval lengths, right? Maybe. So what we did is we said, let's define this new polyhedron in which you drop all the left and right endpoints and you just project it down to this n-dimensional subspace, which is just taking the length coordinates, and that's all you're watching. So now an element of Q is corresponding to a representation here in which a vector will tell you the length of each interval, but it doesn't tell you what the interval is or where the interval is. And we proved this theorem, and it turns out that somebody else also proved it in 2011 before us, but we actually didn't know that when we did it first, and we did it in a completely different way, and we proved a lot more. So it's not a tragedy that somebody else did it before us. In fact, I think it's kind of a good thing because it proves it's an interesting thing. Turns out that this polyhedron is an affine convex cone. It has a single vertex, like any affine convex cone, and that single vertex, the lengths are exactly the lengths in the canonical representation. I think that's very beautiful. And so it has a lot of great consequences, and having only 0 minutes, I don't think I'm going to talk a lot about the consequences here. So just want to say, yeah, there's a lot of stuff left here. So, yeah, this is, for example, what should I say last minute or so? Okay, yeah, this is kind of the techniques that we use to prove this theorem. We have a lot of interesting stuff here. Maybe I should just jump at the end of this section to corollaries. So, okay, so affine convex cone. The affine convex cone is always determined by two things: its vertex and its extremal rays. This is basically a consequence of that Minkowski-Y theorem. I had it on one of the slides. And so once you know that, we know the vertex. The vertex is corresponding to the canonical representation. So we want an algorithm to find its extreme rays. That's actually much harder. We have some beautiful facts about the extreme rays, but we don't know everything. But we do know, we do have an algorithm to compute them. It's not necessarily polynomial, but it's much better than brute force. So it actually works in practice to find these somewhat well. And if the width of the poset is bounded, then we do have a polynomial. So that's a theorem, and that's actually new. I don't think the other people proved any of that. Again, as I said, our techniques are quite different from theirs, and we prove a lot of more general things. So that's one of the things. And what about the interval count problem? Again, we now have one more new algorithm to find out if the poset is a semi-order, because if you can realize that once you know the cone, all you have to know is this vector 1, 1, 1 is in the cone. The vertex doesn't even matter. It's just a geometry reason. It only depends on the cone. So that's a simple algorithm. How about 2 count? Well, okay, I can write down the statement like this, but it's not so easy algorithmically to find out if this is true. So it's the interval order is k count if and only if there are these lengths and k lengths, so that the vector is really just using those k lengths, and then that vector is in the cone, then that's determining if the poset is k count or not. But again, this doesn't really help us in terms of algorithmic, except for special cases. Okay, so some open problems. What's the complexity of the 2 count problem? As I said, that's one of the big open questions. And the k count problem for fixed k could be different. Maybe the 2 count is polynomial, and then up from 3 is not. Sometimes that happens, right? Coloring of graphs, satisfaction problem, 2 set, 3 set, typical thing. But sometimes people ask me, what do I think? And I can honestly say, I have no idea. I really don't know. I think it could go either way. I used to think that the 2 count problem is empty-complete. Then I changed it to polynomial. And right now, I just say, I don't know. Okay, this is another interesting thing. Do the extreme rays form a Hilbert basis for C? So what's a Hilbert basis? Hilbert basis is a basis where every integer point in the cone can be written as an integer conic combination, integer positive linear combination of the extreme rays. So the coefficients are integer. And Andre Kasdy just found this experimentally to be true for every example he tried. We don't have a proof if this is true. I don't know if it probably has algorithmic importance if it's true, because the integers give you nicer computations, but we don't know. So that's all I have. Thank you. Yeah.
Okay, so it's kind of a weird question. Okay, so let's say you have 2 interval orders that have like a small suborders, and they share a common suborder. Let's say.
So they have the same. They have 2. They have the common suborder.
Yeah.
That are the same. Okay.
Yeah. Can you do them together and get still an interval order?
Yeah. No. So I think typically the answer is no to that. So if I understand your question correctly, you take an interval order and you have a representation, maybe one that's desired for some reason, maybe using only 2 intervals or something. And now you take another interval order that also has a nice representation. Can you glue them together to keep the niceness of both representations? And I mean, that's actually no. I mean, in the extreme case, you could say, let's just chop out the interval order into one element posets, right? Those all have a nice representation. Actually, those are all semi-orders. Certainly, you can't keep that property. So, but in general, this is very difficult. And in fact, so a representation of a suborder won't carry over its properties. Sometimes you have to completely redo that suborder in the big poset. One nice thing about that is true for interval orders, and that is only for interval orders, is not true for general posets. That if you have and that's one of the things I skipped over there, that if you have a poset and it has a linear extension, you have an interval order, and okay, let me start. You have an interval order, and then you partition the ground set into some subsets, and you take a linear extension of each of those subsets. You can actually glue those together in a sense that there exists a linear extension of the big poset that keeps the order in every linear extension of these parts. And that's a very powerful and a surprising property, because nothing nearly like that is true for general posets, but it is true for interval orders. And the reason it works for interval orders, because in the proof, you can quickly show that if it's not true, which is actually an easy thing to characterize, then you quickly show that there's a 2 plus 2 poset. So that's a surprising property. That much is true. So maybe it's not completely unreasonable to say nice properties for interval orders are really true. But unfortunately, these length things, they don't ever can be preserved. Yeah, thank you for the question. Nice question. And very natural, right? I mean, why wouldn't you try that? Yes. Yeah. Life is not so easy.
Yeah, no, well, I'm interested in that because when you have some classes of structures that have this property, you can say a lot about them. Well, you can first construct a particular infinite structure that carries most of the properties of the finite ones, and you can say a lot about them at the class with this infinite structure and stuff. So
yeah, so there are lots of kind of a complex property, right?
Yeah.
There are lots of examples of that in combinatorics. Yeah, one of my favorite infinite graph theorems is the Bruin-Erdős, and says that the chromatic number of an infinite graph is less than or equal to k, where it's k, then there exists a finite subgraph that's going to be number k. So those kind of things can be true, but I think it's usually much harder to carry over those properties from a small finite to a large finite than from all finite to an infinite. If somehow the all finite is usually quite more powerful property. Yeah, I think these compactness properties, infinite posets, could be very interesting. We never thought about the count problem for infinite posets or infinite interval orders, but maybe we should, because I think there could be some nice problems and theorems there.
Yeah, this is in fact a little bit stronger than compactness with this as preset here. Remove that, but it's a really particular case of components.
Okay.
Gentlemen, you can also.
Okay.
That's it then.
Yes.
Thank you.